Good morning, students. In the previous lecture, we have covered the metallic conductors, right there, right? And we have seen the usual form of Ohm's law and also the point form of Ohm's law, right? So, just can you recall what is the point form of Ohm's law? J is equal to sigma E, right? This is the point form of Ohm's law. Then we have solved few numericals based on that. And usual form, you know, V equal to IR, right? This thing you know. Okay, then next in today's lecture, we will see the properties of the conductor and the boundary conditions. What are these boundary conditions? We'll see. Right. Then next, we'll see the derivation, that is boundary conditions between conductor and free space. That also we'll see the derivation, and we'll solve few numericals. Right. The next, we'll start with, already you know the properties of conductor. Just as a formality, just I have listed here. Okay, the properties of conductor under static conditions. Yes, whatever we are studying is not with respect to time varying fields, it is with respect to static electric fields, right? So under static conditions, no charge or no electric field exists at any point within the conducting material. Let me take, this is the piece of conductor, then charge Q is 0 and also the electric field E is 0 within the conducting material or within the conductor, right? So the charge means the presence of the free charge carriers within the conductor is 0, right? Charge Q is 0 and the electric field, internal electric field is also 0 within the conductor. This you know it, right? The next point 2, the charge can exist on the surface of the conductor giving rise to surface charge density. Yes, the charges, whatever it is on present on the surface, right? It is given by surface charge density rho s, right? The charges inside the conductor is 0, but the charges are present on the surface of the conductor. Then within the conductor the charge density is 0. Yes, if charges are 0 within the conductor means the charge density is also 0, right? The same thing, first and third point are repeated. Then the charge distribution on the surface depends on the shape of the surface. Yes, the shape can be anything like this surface, right? It can be straight or it can be curved. The surface can be anything, right? So the charge distribution of the surface depends on the nature of the shape of the surface or kind of the surface, shape of the surface. Then the conductivity of an ideal conductor is infinite. Yes, if I consider the ideal conductor, yes, we say that the conductivity is infinite, but practically it is very large for the case of metallic conductors. Then, yes, one more thing, the conductor surface is an equipotential surface. If I consider this as a conductor surface, if I consider point A here and point B here, right, they are at same potential. So conductor surface is an equipotential surface. If I take the potential difference between the 2 points on the surface of the conductor, it will be 0. Potential difference will be 0, right? So these are the, with these 6 properties in the mind, we will try to arrive the boundary conditions between conductor and free space in the next topic. Okay, yes, observe this derivation very keenly. So boundary conditions between conductor and free space. Yes, just observe this diagram, right? So have a look at the diagram. So just one demarcation line has been drawn here. This is the line, demarcation line. On this side, below we have the conductor, below this boundary, and above this we have the free space, right? Conductor and free space. And this is the boundary, right? This is the boundary between conductor and free space. Yes, before analyzing this diagram, just, okay, let me take here. There is a conductor in the below part, free space in the above part, and this is the boundary. Okay, observe here, if I want to make the notation of the fields, let me assume the electric field, you can see the electric field here, E, this is the resultant electric field. It has two components, horizontal component and vertical component. Horizontal component we call it as tangential component, and vertical component we call it as normal component. Okay, so you can observe here the tangential component is tangential to the surface of the boundary. This is electric field, let me call it as ET, right? ET, tangential component of the electric field. Then normal to the surface, perpendicular to the surface or normal to the surface, we will take the normal component of the electric field En. The resultant is in this direction, right? This is the electric field E. So tangential component and normal component. Similarly, we will see with respect to electric flux density, you can observe here, this has been shown here. On RHS, the electric field is shown here, and on left hand side, the electric flux density has been shown here. Observe here, the tangential component of the electric flux density dt, it is tangential to the boundary, and the normal component dn, it is normal to the boundary. So this is the resultant electric flux density. So observe the representation of the electric field and the representation of the electric flux density first. Later on we'll see this diagram, right? Okay. We have seen here with whether it is with respect to electric field or electric flux density D or E, there are two components of the field. One is the tangential component and one is the another is normal component. Tangential component is tangential to the surface of the boundary and normal component is perpendicular or normal to the conductor surface, right? In both the cases you can see here. Okay, next we have to derive what is the boundary conditions. See here, what about tangential component, what about normal component, we'll see, right? For tangential component we will make use of the tangential component of the electric field. What is the condition, boundary condition, we'll see. And for normal component we will make use of the normal component of the electric flux density, right? Just I'm marking here, you can observe here, right? In order to get the nature of the tangential component, right, at the boundary we will make use of the tangential component of the electric field. In order to get the normal component I will make use of the normal component of the electric flux density. I hope it is very much clear now. Okay, we will see one by one. So first let us derive the tangential component of the electric field, right? If I calculate the electric field, I can calculate D. If I know D, I can calculate E because we know the relationship between D and D. D is equal to epsilon naught E. You know this, right? If I know the electric field, I can calculate electric flux density. If I know electric flux density, I can calculate electric field intensity, right? Okay. First, we will try to derive the tangential component of the electric field along the boundary, along this boundary between conductor and free space, right? Okay, for conservative field, let me choose. So this is the tangential component we have taken, right? So around this, we will move the charge in this direction, see here, in this direction like this. So I'll choose some surface above the conductor and some surface within the conductor. So I've shown the path here. Tangential component is like this. So we will choose this path from A to B, B to C, C to D, D to A. You can observe this portion is in the free space and this portion is in the within the conductor, right? So let me call this width as delta W from A to B and C to D, and height B to C or A to D, it is delta H, total height, right? But this delta H is almost negligible and it is equal to 0 means it will come to the boundary only, right? We will assume that delta H is very small so that we are concentrating only on the boundary conditions, right? But this width is delta W. Yes, I want to move the charge along this path from A to B, B to C, C to D, D to A, right? Okay, we know that the sum of Kirchhoff's voltage law, if it is applicable for circuits, the sum of all the potential differences around a loop is equal to 0, right? So the field is conservative if it is equated to 0. That we have seen. This we know. So the closed line integral law, because I am moving from A to B, B to C, C to D, D to A. This is the closed path. Once again I am coming back. So the closed line integral of E dot dl equal to 0. Means we are concentrating on it is conservative field only, right? So we will make use of this equation, conservative field equation. And we will consider the small closed path A, B, C, D, A, right? This path is considered. Then we will integrate this, we will say expand this. Integration from A to B along this line, A to B, next B to C, C to D, D to A. B to C, C to D, D to A, and equate it to 0. Is it fine? We will take one by one. From A to B, what is right? I want the electric field E and the length, right? So we will see here. What is the electric field from A to B? The tangential component is ET. So ET into delta W. So ET into delta W along the path A to B. This is from path A to B. So ET into delta W. Right. The next from B to C. We'll see here B to C. So corresponding to this B to C, there is a normal component, right? So, but normal component is in the upward direction. I am moving from B to C. So minus should come because minus En, because I am coming in the opposite direction. So minus En, right? Minus En into, then what is this distance from B to C? Observe here, delta H. The charge, if I consider the field or charge within the conductor, Q is 0 and field is also 0 within the conductor. So I will not consider this part. So above I will consider the above part. So this distance from here to here is delta H by 2. From here to here it is delta H by 2. So I will consider only this part, minus En into delta H by 2, minus En into delta H divided by 2. Don't worry about this, right? Right, minus En into delta H by 2. So this is from path B to C. Then I will take C to D. But if I take from C to D, since the field is 0 within the conductor, charge is also 0. So C to D, it is not written here. From C to D, let me write it here, it is 0. So it is not shown here. Let me write it here, plus 0. Next, then D to A. Yes, once again, D to A, corresponding to this D to A, the normal component of field is parallel to this, right, is En. So En into, once again, this part, A to B, right, it is, this distance is delta H by 2 and this distance above is delta H by 2. If I consider the field within the conductor, it is 0, so I'll consider only delta H by 2. So in the same direction, that is plus En into delta H by 2. This is from path D to A. I hope you understood. A to B, B to C, C to D is 0, D to A. Right? This is equal to 0. Making use of this conservative field equation. Right? Okay. Next, we'll have rewritten the same equation has been rewritten here. So at B, it is not required. At B, at A. If you want, you can write. Okay. Observe here, En into delta H by 2. This is minus En into, so they will get cancelled. This, both the terms, right? Plus and minus. So what I am left out, Et into delta W equal to 0. So take this delta W this side. So Et equal to 0. If Et is 0, we know the relationship between D and E, right? So D equal to epsilon T. So if Et is 0, dt should be also 0, right? So finally we got the boundary condition, dt equal to 0 and Et equal to 0. I hope this is one of the boundary condition. Means we have derived the boundary conditions for the tangential component. Next, we are still derivation is not over because we have to concentrate on the normal component also by considering the dn. We will see it in the next slide, right? Okay, this is one of the boundary condition. This is the first boundary condition with respect to tangential component is over. Tangential component, right? Okay, from this we will derive some inference. Later on we'll see what is that inference. Okay, next we'll see the normal component, right? So how to derive the normal component? The same diagram, this is the boundary between conductor and free space. So only one diagram, no need to draw two diagrams. Just I've taken the same diagram in the next slide. Conductor is below and free space above the boundary, right? Okay, we'll consider this the electric flux density. dt is the tangential component, dn is the normal. Now we will consider this, right? So we will try to enclose this. So the same with respect. So if this is the normal component, then which is the best Gaussian surface? We will make use of Gauss law. Earlier, for tangential component, we have made use of the field is conservative field. In order to derive the normal component, boundary condition of the normal component, so we will make use of Gauss law. So normal component is perpendicular or normal to the surface of the conductor. So we will take the cylindrical surface, right, enclosing this, right? So it has been shown here outside this, right? So there is a bottom surface, top surface, right, and sides. This is a Gaussian surface, and height is delta H, right? So some part 50%, from here to here it is delta H by 2, from here to here it is delta H by 2, right? Okay. This is within the conductor, field is 0. Above there is a field exists, right? That we'll see. And surface area is delta S, small surface area enclosing this. Okay, we'll see this. So using Gauss law, closed surface integral of d dot ds equal to q. Right, this is the Gaussian surface, right? This is the Gaussian surface. It is enclosing some charge q. So we know that the charge is present on the surface of the conductor here, right? Within the it is 0. Above it is also it is 0, right? Within it is 0. So the charge, surface charge is present only on the surface of the conductor here. So let me call the total amount of charge enclosed by this Gaussian surface, or by Gauss law, we can write it as closed surface integral of d dot ds equal to q, right? And we have to integrate throughout the entire surface. So it has sides of the cylinder, top surface and bottom surface. So top surface, bottom surface and sides. But since the charges are residing only on the surface, so we will consider only the top surface. Means here this delta H is almost approaching 0. Means if it is approaching 0 means I will consider only this, only top surface. Sides are absent, and bottom, if I consider this, it is 0 because charges lying inside the conductor is 0. So we will discard this bottom as well as sides because delta H is almost approaching towards 0, means it is approaching the surface or boundary. Alright, so I have only the top surface, right? So on the top surface, what is D and what is ds? So D is the field living normally to this, means dn. This is dn. right? The normal component of electric flux density. And what is this surface area? It is delta S. So multiply dn into delta S. So dn into delta S. Only for considering the top surface. dn into delta S is equal to Q. What is this Q? It is surface charge density. Express this Q in terms of surface rho S into ds. Rho S into ds is nothing but delta S, right? Rho S into delta S. So Q is equal to rho S into delta S. So cancel this delta S, delta S. So finally I will get dn equal to rho S, right? So what about En? We know that d equal to epsilon naught E. So d equal to epsilon naught E. So I want normal component of electric field intensity. So En I want. So En equal to what? So d divided dn divided by epsilon naught. So what is En? En is equal to, or else I will write En into epsilon naught equal to dn. Is it fine? So epsilon naught En equal to rho s, that is equal to rho s. So in the next slide it is written. So this is the first boundary condition, and second boundary condition dn equal to epsilon naught En, that is equal to rho s. First boundary condition and second boundary condition. This is with respect to tangential component, and this is with respect to the normal component. I hope you understood the derivations. If any doubts are there, please unmute yourself and speak to me. So these two boundary conditions, we will see. We have derived some characteristics or properties from these two equations. We will see. The static electric field intensity inside a conductor is 0. Yes, within the conductor, the electric field E is 0. This we know. Using this concept only, we have derived these boundary conditions, right? Yes, E inside a conductor is 0. Next, the static electric field intensity at a surface of a conductor is everywhere directed normal to that surface. If this is the surface, the electric field or electric flux, it is always normal, perpendicular, right? Always. If it is in this direction, this is normal. I hope you understood. It is everywhere perpendicular or normal to the considered conductor surface. Then conductor surface is an equipotential surface. Hence, we got the first condition. See here, dt equal to 0. Observe here, if I locate one point here and point here, point A and point B, they are at the same potential. So the potential difference is 0. So this dt equal to Et equal to 0. This is first boundary condition. What it will tell? The conductor surface is an equipotential surface. Hence, the tangential component of the field is 0. Right? These are the three properties or characteristics what we have derived from these two equations. Right? Okay, derivation is over. If any doubts are there, please you can ask. For tangential component, we have made use of the field is conservative. E dot dl equal to 0, and we have chosen the path A to B, B to C, C to D. A, B, C, D, A. Right? Just I am giving you the hint. And we have made use of Gauss law for this normal component. So closed surface integral law of D dot ds equal to Q. And we have considered only top surface. Right, and we got dn equal to rho s, that is equal to epsilon tn, right? Okay, we'll solve few numericals. Given the potential field V is given, that is 100 into x square minus y square, and a point P, yes, 2 minus 1 3, that is stipulated to lie in a conductor to free space boundary. Yes, let me take this as a conductor to free space. This is the boundary, right? And let me assume that conductor is below and free space is above, free space, right? Just rough diagram I'm drawing, not exact diagram. And point P is lying, let me assume point P is lying somewhere here, 2 comma minus 1 comma 3. It is on the boundary, right? Lie on a conductor to free space boundary. It is lying on the boundary. Let us find out the potential V, the electric field intensity E, D, and rho s at point P. Right? All these parameters we have to find out at this point. And also the equation of conductor surface. Right? We'll see. This is the equation of conductor surface already, but let us find out V and substitute. That will form the equation of the conductor surface. That we'll see one by one. Solution. Yes, find out V at point P. At point P, what is the potential? That is V at point P. Substitute the value of x by z in this equation. Right, we will get the potential at point P. So 100 into x square, that is 2 square, minus y square, that is minus 1 whole square. Right, we will see. So 2 square is 4. Then minus 1 square is 1, 4 minus 1 is 3, 3 into 100, 300 I will got, 300. So Vp equal to 300 volts. This is the potential at point P, this is over. Next, the electric field. Let me call it as part A and part B. A is over, next B. So electric field we want to find out. So how to find out? E is equal to the gradient, right? Minus del V, right? So we know the V equation 100 x square minus y square. So first we'll find out del V. Since this is a Cartesian system, so gradient of a scalar point function is a vector dou V by dou x into Ax plus dou V by dou y into Ay plus dou V by dou z into Az. So we will write down V. Just I will multiply 100 x square minus 100 y square. So differentiate this with respect to x. 100 into 2, 200 x nx to the power of n minus 1, right? Okay. Minus. So thus with respect to x means this will be 0. We will leave it. Then into ax plus we will come to the second part. With respect to y I have to differentiate. This term will be 0. So I will be getting minus 200 pi into ay. Then next, this is the v. Differentiate with respect to z means this will be 0. Leave it. Right? So at point P I want. So at point P we will do it later. So E vector is equal to minus del V. So minus, this is del V. So minus 200 x into Ax minus into minus, this is plus 200 y into Ay at volt per meter. This is the right. So next I want at point P. At point P. So what is E? So E vector at point P. Substitute the value of x, y, z in this. So and write the x is, so I will calculate and write x is 2. So minus 200 into x is how much? 2. So minus 400 I am getting. Minus 400 ax. Next plus 200 into y. What is y? Y is minus 1. So minus 200 ay volt per meter. Right? So this is E at point P is over. Next part C will see D. Part B is over, part C. Find out D vector. So D equal to epsilon naught E. Is it fine? Okay. D equal to epsilon naught E. So already let us find out at point P only. At point P, D at point P is equal to epsilon naught E at point P. So epsilon naught is 8.854 into 10 power minus 12 into E at point P is minus 400 AX minus 200 AY. I have made some mistake. Let me check. Yes, this is plus side. No, it's correct only. It's minus. Yes, correct. Minus 200 AY volt per meter. Okay, fine. Then D at point P, just multiply 8.854. 10 power minus 12, you can take it out and write it. So minus 400 into 8.854. So I am getting it as minus 3541.6 AX. Then I will multiply 8.854 with 200. 8.854 into minus 200. So I am getting it as minus 1770.8 AY into 10 power minus 12. This one I have to write 10 power minus 12 coulomb per meter square. Right? Okay. This is D at point P. This is over. Next, find out rho s point P. This is the last one. So D. Rho s at point P. Yes, it is asked to find out the surface charge density here at point P. Rho s we want to find out. Right? So observe we can use one of the boundary conditions what we got here. So dn equal to rho s, right? So dn equal to rho s. So if I want rho s, it is equal to dn, the normal component of the field. So what is this? We have to find it. What is dn? Observe here, we got d vector at point P, right? So I want only normal components. Just observe here, since point P is lying on the boundary, right? What about tangential component? It is 0, et is 0. So I don't have any tangential component. Only what is the d vector I have? It is nothing but dn only, dn into an, right? The normal component. Whatever the d vector, it is only normal component. I don't have tangential component because tangential component is 0 on the boundary, because we know this dt equal to et equal to 0. Tangential component is 0. So if I want to write out d vector, so tangential component dt plus the normal component dn. If I want to write in terms of electric field, so the tangential component of the field et plus the normal component of the field en. But here in this case, the tangential component is 0. That's right. So d equal to dn vector. So here e equal to en vector. I hope you got it. So whatever we have found out dn or d, these are all only normal components. So I want rho s equal to dn, the magnitude. Right? Take the magnitude under root of this square plus this square, right? So under root of, so dn equal to under root of minus 3541.6 into 10 power minus 12. This one is the right whole square. 3541 whole square plus minus 177.0.8 into 10 power minus 12 whole square. You do this, you will get rho s. So under root of open bracket minus 3541.6 exponential minus 12, its square, plus open bracket minus 177.0.8 exponential minus 12, its square, close bracket. So its root I am getting it as rho s is equal to 3.95 into 10 power minus 9. So coulomb per meter square. Right? So I have written the answers in the next slide. We'll verify. Right? So yes, one more thing is left out. Also find the equation of the conductor surface. This is the equation, but what is V? We have found out that is 300 volt. So part E, equation of conductor surface. Equation of conductor surface. So substitute V equal to 300. So 300, it is equal to 100 into x square minus y square. This equation, right? So what is x square minus y square? X square minus y square equal to, so 3. So this is the equation of the conductor surface for the conductor surface, right? X square minus y square equal to 3. Okay, we'll verify one by one with 300 volt. Then EP at point P minus 400 AX minus 200 AY minus 400 AX, right? Then next dp, right? So in terms of nano they are given, but I have written in terms of 10 power minus 12. This is also correct. Then rho s at dn, that is 3.96 nano. Just observe here, 3.95 means 96 nano, right? We got this. This is also correct. Rho n, right? And conductor surface x square minus y square equal to 3. Solution I have given in this slide. Okay, we'll take up the next numerical. Right? Given the potential field V is equal to 100 sine hyperbolic. This is hyperbolic. Sine hyperbolic 5x into sine 5y volts. This is volts. And a point P is given. Find at P. We have to find out all these parameters. V, electric field, magnet, right? All those things what you have done in the earlier case. And P lies on the conductor surface, right? Once again, this is the, let me assume this is the conductor is here, and free space. No need to draw the diagram, but let me be clear. And this is the boundary. Boundary between conductor and free space. Point P is given. Right? It is 0.1, 0.2, 0.3. It is lying on the conductor surface here on the surface, right? Or on the boundary also we can say. Yes, we will find one by one. Part A, find potential at point P. At point P, so what is V? V at point P. Substitute the value of x, y. This is x, y, z. We'll substitute here. So observe here, keep your calcium calculator radians mode, because sine hyperbolic 5 x is 0.1. So first, please, I have written here for just for hint. So keep your calcium radians mode first before calculation, right? So go to radians mode. So keep your calci in radians mode. Yes, I have kept my calculator in radians mode. Then next 100 into hyperbolic sine I want to see here. Hyperbolic is there. So first press hype on your calculator, then press sine. So I'm getting sine hyperbolic, open bracket, 5 into x. X is how much? X is 0.1. So this is over into. The next sine 5y into sine, open bracket, 5 into y. Y is how much? 0.2. So I'm getting it as 43 point after substitution here. And first keep your calc in radians mode, then substitute the value of x and y and calculate. So I'm getting it as 43.848 volts, right? Over. Then part B. So E equal to minus del V, right? So first we'll find out del V, then we'll take minus sign. First, gradient of scalar point function. So observe here, del V. I should write the formula of del V in which system? Cartesian system only, right? Everything is in Cartesian. So gradient of scalar point function is a vector. Dou V by dou x into Ax plus dou V by dou y into Ay plus dou V by dou z into Az. So we will differentiate with respect to x. So with respect to x means 100 sine 5y is constant. 100 sine 5y is constant, right? So differentiation of sine hyperbolic 5x, right? Cos sine hyperbolic x is cos hyperbolic, right? So cos hyperbolic 5x. Since 5 is there, multiply 5 here. I have taken 5 this side, right? Over into ax. Plus next differentiate with respect to y. So with respect to y means 100 sine hyperbolic 5x is constant. So differentiation of sin x is cos x. So cos of 5y. So into 5. So I am multiplying 5 there. 5 into 100. 500, right? This 5. The next with respect to z. So if with respect to z means this is constant. So I am getting third term as 0. So let me write it here. So what I am getting E minus del V. So I'll take minus sign. So just multiply minus sign for this del V. Minus 500. 5 into 100. 500 sine 5y into cos hyperbolic 5x into ax minus into plus minus 500 sine hyperbolic 5x into cos 5y. Yes, one more thing I have missed out, ay. Please correct me if I am making any mistakes. Don't keep quiet. So volt per meter. Right, now at point P I want. So substitute the value of x, y, z. X is 0.1, y is 0.2, z is 0.3. Substitute here in this and write down. So E vector at point P is equal to. So I'll substitute and write finally. So keep your calc in radians mode only. Let it be in radians mode. So minus 500 into sine 5y. Sine 5 into y. Y is how much? 0.2 into cos hyperbolic cos, open bracket, 5x. 5 into x is how much? 0.1. So I have calculated first term. So I am getting it as minus 474.43243 ax. Next I'll take the second term, minus 500 into hyperbolic is there. First hyperbolic sine. So into 5x. 5x is how much? 0.1 into cos y, cos 5y I think. Yes, let me check it. I have done somewhere mistake here. Cos 5y is there. I have left 5 here. Please observe all such mistakes, right? Cos 5y is there, right? Okay, cos of 5 into y. Y is how much? 0.2. So after calculation I am getting it as minus 140.77 ay. volt per meter. Right, so first one is 43 point, this is over. Second one, observe, minus 474 ax minus 140.8 ay. So part B is also over. Next, magnitude of E, part C. So magnitude of E, find out magnitude of E vector at point P. Magnitude of E vector at point P. Right, so under root of 474.43 square plus minus 140.77 whole square. Right, so find out the magnitude. So under root of 474.43 square plus 140.77 square. 140.77 square, close bracket. So I am getting it as 494.87 volt per meter. Just you can check part C. So 494.87 round it to, so it is 495. This is over. Next, part D, magnitude of rho s, part D. So no need to tell magnitude of rho s, it is rho s is magnitude only, right? So how to find out rho s? So we will make use of boundary condition, right? So dn equal to rho s, right? So rho s equal to dn. So what is dn? So since the point is lying on the boundary, so the tangential component is 0. Whatever the d vector is there, it is nothing but the normal component only, right? Tangential component dt is 0, dt vector. So dt plus dn, right? So only it is d equal to dn only, because dt is 0. So we already know E vector, and one more equation I can write. So rho s equal to dn. I can write it as epsilon naught en, right? This we have seen. Dn equal to epsilon naught en, that is equal to rho s, right? So epsilon naught en. So then what is E vector? E vector is equal to en only, because tangential component et is 0. By making use of boundary conditions, tangential component et is 0. So whatever the field I have, it is normal component only. So we will make use of this. This will be very easy. Rho s equal to epsilon naught en. What is the magnitude? We got en. So it is 494.87. This is en only, right? So 494 into 494.87. So what is epsilon naught? Substitute and calculate and write. So epsilon naught is 8.854 into 10 power minus 2. So just multiply this and write it. So 8.854 exponential minus 12 into 494.87. So this is, I am getting it as 4.38 into 10 power minus 9, right? Coulomb per meter square. Right, you can check it. 4.38 nano coulomb per meter. Nano means 10 power minus 9. I hope you got it. Yes. Okay. So here in this problem, through first this problem and previous problem, we are making use of boundary conditions to find out the surface charge density, right? So the two boundary conditions, just once again I am writing here, just as a quick review. So et equal to dt equal to 0. Tangential components are, this is the first boundary condition. Second boundary condition is dn, which is equal to epsilon naught en, which is equal to rho s, right? So for conductor to free space, this is conductor and this is free space, and this is the boundary, right? So these are the two boundary conditions, dt equal to et equal to 0, dn equal to epsilon naught en, that is equal to rho s. So in the previous two problems, in order to calculate the surface charge density, we have made use of the boundary conditions, right? Okay, we'll take up one more problem, the last numerical of today's class. This is the last numerical. Okay, this is the answer. We'll discard it later on, we'll see, verify, right? Okay, a potential field V is given. V is equal to 100 e to the power of minus 5x into sine 3y cos 4z volts. Let point P, that is 0.1 pi by 12 pi by 24, be located on a conductor to free space boundary. At point P, find the magnitudes. The same thing what we have done, but in this you can see here, V, you can find out what is tangential component, what is normal component they have asked. This and what is dn, all these things. We should be very clear. We'll see one by one, right? Okay, V is given. Part A, we'll see. V at point P. find out V, right? First, so V at point P, let me call it as, so substitute the value of, so here see here x y z, so if by looking at this I will come to know this is r theta phi, right? But observe here, this is pi by 12, I am, let it be, pi means 3.141 like divided by 12, so I will treat this as x y and z only. Substitute the value of x y z here in this and write down what is the potential, right? So keep your calci once again in radiance mode. Calci should be in radiance mode. Radiance mode. Keep your calci in radiance mode. So already my calci is in radiance mode. So I'll substitute the value of xyz in this equation, right? Okay. So I'll calculate here. I will make the equation 100 into e to the power of shift e to the power of minus 5 into open bracket x is how much, 0.1, so no bracket is not required, minus 5 to 0.1 close bracket, then into sine of 3y, 3 into what is y, y is pi by 12, 3 into pi by 12, shift pi divided by 12, so close bracket, then next into cos of 4z, 4 into z is how much, z is pi by 24, 4 into pi divided by 24, so I am getting it as 142 volts, right? So you can verify 37.1422 volts, right? So first one is over. Next we'll calculate E. We know how to calculate at point P only, E vector equal to what, at point P, right? So we know that E equal to minus del V. So we will write down the gradient of scalar function del V in rectangular coordinate system only, because we have x, y, z, right? So del V, gradient of scalar point function is vector. We know this formula, dou V by dou x into ax plus dou V by dou y into ay plus dou V by dou z into az. So we'll try to differentiate and write it. So with respect to x means 100 sine 3y cos 4z is constant. So let me write that 100 sine 3y into cos 4z is constant. So differentiation of e to the power of minus 5x is e to the power of minus 5x and multiply minus 5 here. Minus 5 into, right? Minus 5 into 100. Okay, into ax. First term is over. Next, with respect to y. So with respect to y means, so 100 e to the power of minus 5x cos 4z is constant. So let me write it, 100 e to the power of minus 5x cos 4z. So differentiate with respect to y. Sin y is cos 3y, cos 3y. So this 3 will be coming, 3 I will multiply, 3 into 100 is 300. Let me make it 300, right? This one, right? Over into ay. Then next last term with respect to z. So this entire thing is constant. So plus 100 e to the power of minus 5x into sine 3y. So this differentiate with respect to z. Differentiate of cos x is minus sin x. So this minus will be coming here. So instead of this minus I'll write, so sine of 4z, but 4 is there, multiply 4. This will be, this I will make it 400. This I will make it 400, right? Okay, into az. Okay, next I want E vector at point P. So E vector equal to minus of this, right? So minus, so let me write E vector first. So minus, I have to multiply minus into minus, this will be plus. So 500, 100 into 5, 500 sine 3y cos 4z e to the power of minus 5x into ax. Then minus into plus, this is minus 300 e to the power of minus 5x cos 4z into cos 3y into ay. Then minus into minus, this will be plus because minus del v equal to minus del v, right? I am multiplying minus. So 400 e to the power of minus 5x into sine 3y into sine of 4z into az. So at point P, substitute at point P. So what is E? E vector at point P I want, right? So substitute the value of x, y, z and write it. So finally we'll calculate. So x is 0.1, y is pi by 12, z is pi by 24. So if your calci should be compulsorily in radians mode. Already I told calci should be in radians mode and calculate. So first I will calculate one by one. First this term, entire thing I will calculate and write. So 500 into sine of open bracket 3 into y. Y is how much? Pi by 12. 3 into pi divided by 12 into next cos of 4z. Cos open bracket 4 into z. Z is how much? Pi by 24. Shift pi divided by 24 over. Then what I am left out? So e to the power of minus 5x, this one. So into e to the power of shift e to the power of minus 5 into x is how much? 0.1. So after calculation I am getting it as 185.71 ax. Similarly I will calculate this entire thing minus 3, right? So minus 300 into e to the power of shift e to the power of minus 5x. Minus 5 into x is 0.1. Yes. Then next is cos of 4z into cos of 4 into z is how much? Pi by 24 into pi divided by 24 into next term is cos 3y into cos open bracket 3 into y is how much? Pi by 12. Shift pi divided by 12. So I am getting this as minus 111.426 ay. Similarly I will calculate this third one. So calculations are very big, that's all. 400 into shift e to the power of open bracket minus 5 into x is 0.1 into next sine 3y. Sine 3y, yes, sine of 3 into y is how much? Pi by 12. Shift pi divided by 12 into this is over. Next sine 4z. Sine of 4 into z is how much? Pi by 24. Shift pi divided by 24. So I am getting this as 85 point plus 85.776 az volt per meter. Just verify this. E vector at point P, this is over. Part A is over. Next part B is also over. Part B is also over. So part B answer you can check it here. 185.7 minus, right, volt per meter. I hope you got it. The next tangential component, part C, they have asked. Part C. Observe here, this is conductor to free space boundary means since point P is lying on the conductor to free space means what is the tangential component? ET we have to find out, right? So what is total E? E is equal to the tangential component of the field plus the normal component of the field we know. But what about this tangential component? It is 0. Boundary condition, ET is 0. So this ET is 0 means what is E vector? It is nothing but En only, right? So what about tangential component? So directly they have asked means ET equal to 0 I have to write. That's all. Over. This is concept based because since the point lies on boundary, since point P lies on boundary. So the tangential component ET is 0 over, right? Then part D, right, tangential component ET equal to 0 over. This is over. Next En they have asked. D, En, what is En? So we know that E vector is equal to ET plus En. So since tangential component is 0, E equal to En, right? So but what I want magnitude of En. So magnitude of En means just find out magnitude of E, that's all, right? Already I have E vector at point P, just find out its magnitude. So E vector at point P I have, So find the magnitude of this vector, right? Under root of 185.71 square plus this square 111 square plus this square. So we'll calculate this under root of open bracket 185.71 square plus 111.426 square plus third one 85.776 square. So close bracket. So I'm getting it as 232.94 volt per meter. So this is the normal component, right? Let me verify, right? 232.92. Yes. So this is over. Next, calculate d vector. So we know that relationship between d and d vector at point p, d vector is equal to epsilon naught e vector at point p we have, right? So what is epsilon naught? 8.854 into 10 power minus 12 open bracket. So write down e vector at point p. I have this 185.71 ax 185.71 ax minus 111.426 ay plus 85.776 az, right? So multiply it and write it. 10 power minus 12 I will keep it outside, so just I will multiply 8.854 and write it, right? So 8.854 into 185.71. So I am writing 1644.27 ax. 10 power minus 12 I will write it last, minus 8.854 into minus and already taken care 111.426, right? So I am getting it as 986.565 ay. Then next I will multiply 8.854 for the third part 85.776. So I am getting it as plus 759.46 az. This entire thing into 10 power minus 12, this I have left out, right? Into 10 power minus 12 coulomb per meter square. So this is d vector. Just check it. Yes, they have given only magnitude. D vector, then yes, it is there. I think yes, 1588, but I am getting 1644. Just check it. Epsilon naught p. Just multiplication is correct. 185. I have not missed anything. Maybe this answer may be wrong, right? Maybe this answer may be wrong. This answer is correct because calculation is correct here. So let me take pen here. Or else you try to do it once again. This answer is correct, right? Because d equal to epsilon naught ep, right? That we have done. That's correct. E is correct means E is correct here. Means they have calculated d wrong. They have calculated d wrong, right? So I think this is correct. While multiplication I have done it properly only. If any mistakes are there, please you can speak to me. If it is correct, I will proceed. Yes, part F. So the answer is not matching here with this. Please check it. Okay, next what they have asked, dn, right? So dn means whatever the d vector itself is dn. So find out the magnitude of this under root of this square, 16 this square plus this square, right? The same thing we'll do under root of, just I'll write it here, dn equal to under root of 1644.27 whole square into 10 power minus 12 whole square plus minus 986.565 into 10 power minus 12 whole square plus 759.46 into 10 power minus 12 whole square. Got it? The magnitude of this only, right? It is normal component only, dn vector. D vector is equal to dn vector. So find out magnitude, so you'll get dn. So root of open bracket 1644.27 exponential minus 12 square minus 12. Let me make use of brackets. If instead I will make use of another bracket here. Okay, this is square plus open bracket 986.565 exponential minus 12, this is square, plus open bracket 759.46 exponential minus 12, this is square, close bracket. I think I've taken my exponential minus 12 everywhere. Yes, it's fine. So I'm getting it as dn is equal to 2.06 into 10 power minus 9 coulomb per meter square, right? So answer will be not tally because they have done with this vector itself is wrong, right? So naturally they will get it is wrong here. So 2.06 into 10 power minus 9, right? So 1.992 is almost 2, but this they have calculated wrong, right? So this is over. Then they have asked rho s. So part G, rho s is equal to what? We know the boundary condition. It is equal to dn. Dn already we have found out, this only the same thing. So 2.06 into 10 power minus 6 coulomb per meter square, right? So this is over. So I'll stop recording.